So to get us started, to really kind of get us anchored, I'd like to get a feel for where you're all at in your reactions, your reflections about AI. And so what I'd ask you to do, and if you would be willing, that would be great to put this in the chat. I'd like to hear what is your best quote about AI. This can be your own, something you just generate right now or that you've generated before, or this can be someone else's that you really like. But if you wouldn't mind throwing your favorite or your best quote about AI into the chat for all of us, that would be great.
So, wave of the future, the path is on now, is not inevitable. AI is coming for your job. Game changer. AI is super helpful. Use it as your thought partner. Powerful research tool that still needs human quality assurance. It's revolutionary. Allows me to do things I never thought possible. I fixed my own computer. Great, Janice. A new superpower. Okay.
Great. Thank you, Doug. Okay, so thank you all for getting us started on that. So, already heard some great themes in there, and I think it would be interesting to compare what you all had and your reactions to what AI has to say. So, let's take a look at the three frontier models here. So, I asked ChatGPT recently the same question, and ChatGPT's answer was artificial intelligence is humanity's first tool that can amplify not just our strength, but our imagination. And that makes wisdom more important than power. So very interesting that there's some, I think, some alignment in the themes, some of the themes I've heard so far, which is this idea of this powerful tool, and it's all about amplification. But I'd also like to note, you see right there in that first part that ChatGPT is about imagination or creativity. So really a couple good themes there coming out already. Gemini, which is coming from Google, has a pretty similar answer as well. So their best quote is that artificial intelligence is not a substitute for human intelligence. It is a tool to amplify it. So what's I think interesting about that again is a very similar theme. It's about amplification, but also maybe even a bit more defensive. Really taking the standpoint of doesn't want to be a threat to humanity. So don't worry, not going to be a substitute. And then follows it up here saying the real magic happens not when machines think like humans, but when humans use machines to think bigger. So just more on that amplification theme. Okay, so a lot of similarity there between ChatGPT and Gemini. Claude Sonnet, coming from Anthropic, had really quite a different response. So Claude Sonnet said, the question is not whether machines can think, but whether we can think clearly about machines. And in fact, then unsolicited, it followed up with a bit of a justification for its response. And really kind of goes into this idea that we spend a lot of energy debating whether humans and machines think similarly, but really we need to be more precise about what we actually mean by intelligence and thinking and understanding and creativity in the first place, which again is a pretty interesting different approach. So I think this is a great just first theme, which is the frontier models or really any other AI models have a lot of similarity in how they work, how they are built, how they function, but there's also quite a bit of difference between them as well. And we can see that even in asking about its best quote. I thought it was only fair if I'm going to ask you to come up with a quote. I had better come up with one myself. So here would be my best quote, which is that AI is a transformative technology. We're seeing that happen in real time. And we humans need to continuously reflect and then act on how we wanted to transform our education, work, society, and lives. And so, what I really wanted to bring to the fore, again, is our locus of control and really acting on how we'd like AI to change the world instead of being passive passengers. Okay, so I'm going to ask you to do yet another thing today. And this one, you really don't need to put this in the chat. This is really just for you and to get an idea of where your understanding is currently with how AI works. What have you heard? What have you read? And so why don't you give that a shot wherever you'd like to. This can be on your phone, notepad, wherever you're taking notes. But I'd like you to write out a three-ish sentence explanation of how you think or how you know AI works at this point. So I'll give you about a minute to do that. and then I'll give a little more guidance. Yeah, let's take a few more seconds to get down your last thoughts. Okay. So I thought what would be helpful is now that you get a sense of where you're at on this understanding, I'll go ahead and give my best attempt at a paragraph answer to this. And then I'll give a little more guidance on, where we can get in our understanding, in the hour that we have together. So my answer would be is to first ask you to consider how you have learned over time, from childhood to today. So if you just reflect on that, you listen, you observe others, you learn from others, you read, you make mistakes. And when you see that same context, you try not to repeat those same mistakes. So when you're asked on that second date, you're asked to do that favor that is promised that won't take that much time. You see that context that may be similar to what you've seen before, and you try not to repeat. So in other words, you learn from your experience in the world. There is an analogy for how AI learns as well. So AI learns from its input data, which is billions of text, images, and videos and other modalities. That's kind of like AI's experience with the world. And it then uses billions or trillions of parameters to try and then accurately reproduce this input data. And essentially, what it's doing is it already kind of has the answer key. It has all of these texts and all of these documents, and it intentionally removes a part of those documents. And it's simply trying to fill in the blank. So it kind of covers that. You can imagine, teaching yourself and covering up a portion of the page as you're trying to learn. So it covers that up and then it tries to accurately reproduce. And it's just tuning those little knobs, those parameters to the right settings to get it right as much of the time as it possibly can. That way, when it then sees a new context that it hasn't seen before, it can then search its vast storehouse of input data and match this new context to the most similar context it has seen, and then just makes its best educated guess on what to output, what you may be looking for. So again, I just want to draw that analogy in learning from mistakes and learning from trial and error. There is some similarity there in how AI does work under the hood, but I don't want to say at all that it is the same as the way that we learn either. So, there's a lot to understand on how AI works. So, what I thought I'd do is tackle this with three questions that I hope we can answer and that you can answer by the time we're done here. So, one question I'd like to be able to answer is how does AI represent meaning in context? What does that look like when we look under the hood? Then I'd like you to be able to pick a component of an AI model. We'll see a number of its components and see if you can explain how it makes it better, how that component makes AI better at representing nuanced meaning and context. And then finally, I'd like us to be able to answer what is ground truth? This may be a term you've heard, maybe not, but what is ground truth and why is it so fundamental to understanding how AI works? So maybe those are ways we can kind of orient on how we can answer such a big question today. So I'll start with a bit on the origins of AI, just a brief historical treatment that will anchor us and just help us understand how AI works today. A lot of the vocab, no one wants to hear me lecture on a bunch of vocab today, so I won't do that. But you will get some new vocab probably along the way, and I'll try to define it as we go. If there's a term you're getting hung up on or I didn't explain, again, feel free to ask that in the chat. I'm happy to discuss it at any time. I also provided ahead of time, and I think maybe this was sent out ahead of time, a glossary of 102 really core terms to AI. So you can feel free to refer to that as well. Then we'll take a look under the hood at large language models and how they work, and hopefully should have plenty of time for discussion when we're done, both throughout and then when I'm done today. But again, I want to emphasize at this point before I get launched again, if there are questions, you're getting hung up on something you really want me to address in the moment, happy to do that. I think Jasmine is monitoring that chat and can let me know. Okay, so origins of AI. I think a good place to start is with Alan Turing, considered one of the progenitors of computer science, of the computer itself, machine learning, some of the core mechanisms of how AI works. But the part I'd really like to focus in on is what we now call the Turing test, because you're going to see its similarity to a lot of how AI gets evaluated today. You can see his fingerprints really all over it. So what Alan Turing did was he really reframed a lot of the questions at the time about computing. And the questions at the time were, can we get a computer or an algorithm to think like a human? Is there a way to really even examine that? And while an interesting question, one I think we should still explore, Alan Turing said, let's actually reframe that instead and look only at the output from a human and a computer. And if those are then comparable or in fact impossible to distinguish, then we call that passing the Turing test. So that becomes more of an outcome focused approach, which I think really it continues today in how we think and evaluate AI. All right, so let's look at one of the first foundational bricks of how AI really works under the hood, and that is in the field of what was termed latent semantic analysis. And the latent part here refers to uncovering hidden themes from a large body of text. So we could imagine is let's just take all of Wikipedia and we put that together in one big corpus. And what latent semantic analysis was designed to do was extract all the themes that come out of all of those disparate documents and articles. And the way that it did that, I think, is really helpful to understand. So I'm going to go just a little bit into detail without the math, but just look to see how this actually works. And so the way this works is, as you can see, if we focus here on the upper right, what I do is I take all my documents. Here I have 6 documents. You can imagine, again, thousands of documents coming from Wikipedia, and arrange those each in a column. And then on each row, what I do is I take every single unique word that existed in that corpus of documents. And I'm simply going to go into these cells here, and I'm going to count up the number of times each of those words occurred in each document. And when I arrange these documents by the order of those frequencies, you can see something very interesting start to happen. So take a look at this diagonal. I've shaded it darker color here, black to show where the higher frequencies are. What you can see happening is that on the diagonal, these themes are presenting themselves. And so what happened is we simply look at the co-occurrence of words that tend to co-occur in the same document. So like air, climate, conflict, and environment, that theme is probably articles about climate change. And then we have college and party. Those are happening a lot in document 3 and 5, but not so much in 1 and 6. So those must be about, a college party of some kind. And then, we have lemonade and sunscreen, probably some documents about, the summer. And so what I really want to key in on here is this was a first look at how to look at the context surrounding words. In this case, it was just what words tended to co-occur in the same context, in the same document, and use that context in some very useful way. In this case, you could use this for information retrieval. So if I want to go, okay, I want to learn all I can about climate change. Well, now we have a way, we just go to documents that have the same words in them. And we can then use that as a searchable tool. So 2 big things. One, this was our first look at how to use the co-occurrence of words together in a context to really accomplish a very complicated task of search. Okay, so there's one really important link in the chain. That's 1997. Let's fast forward to Mikolov in 2013. So just over 15 years later, we have our first neural network. And this requires a new kind of concept in how we think about context, at least a new way to quantitatively implement it. The idea was actually quite old and has been around for a while, and I'll focus in on first version of this from the 50s. And what Frith said was that if you really want to understand meaning, you want to understand what a word means, we should look at the company it keeps. So, meaning, look at the context around that word. So, if we understand what a dog really is or what a dog means, the beginning point might be a dictionary definition, but that is certainly not the end point, according to this theory. The end point is really thinking about all the context that dog gets used in, pet, leash, family, best friend, and so forth. That is how we really get a deeper representation and understanding of what a dog really is. So, what this first neural network accomplished for us that was really not possible before is what I'd like you to imagine you have a sphere. And in this sphere is every concept that you've ever been exposed to, every concept that you know, maybe every concept that's been written down. And in this sphere, then, we have these geographical locations of each concept. So you can imagine in the upper right of this sphere, we have I walk my dog, across the block. And then that would be in that upper right coordinate system. As we go down to the lower left, it's like I'm preparing for, the GRE, or the MCAT or something. Sorry, that's on my mind for, end of the academic year here. So two totally disparate conceptual ideas can now be represented as a geographical set of coordinates. So imagine it like latitude and longitude, but now it's for concepts. And the way that actually gets represented is what's called an embedding. So you may have heard that term, a word vector or an embedding. That embedding is that quantitative representation of where that concept falls in that sphere of conceptual space. And so again, I promised we look under the hood, so let's go ahead and look. What does an embedding actually look like? Well, right here in the middle of the screen, where you can see this long string of numbers, that is essentially a very precise coordinate location of where that word fits in that conceptual space. It's just a long string of numbers. And what I did to make it a little bit easier to process is I turned these numbers into colors. And so you can see darker reddish colors, that's a positive number. The coolish bluer colors is more of a negative number. And so now you can get a feeling for what these numbers are visually. So now let's go ahead and skip to the upper right-hand portion of the screen, and let's take a look at what these embeddings then look like. So here's an embedding for the word walk, again, represented by all these numbers, and then an embedding for run. And as you can see, there are a number of locations here where there's a lot of overlap. They're very similar. Again, the idea being is because they're often used in similar contexts. You can imagine exercise, diet, health. So when it's used in those similar contexts, the embeddings themselves end up looking very similar. So if we think back to that question we want to answer, how do these models represent context and meaning? This is one of those first answers. They represent it with these embeddings, these numerical values that place it in a coordinate system that we can then quantify and do something with. Okay, so that was our very first neural network. And the reason it got the name neural network, by the way, is to draw an analogy for how neurons work and that they tend to be very interconnected. So you can have a lot of inputs going to a lot of outputs. So that general analogy is also how these embeddings work. Okay, let's fast forward again. Oh, actually, no, let's take an actual look. I thought it might be helpful to look at an actual conceptual space. So this is a 3D rendering of that conceptual space I talked about. And you can see the words suburb, city, and towns all are in a very similar location in this conceptual space versus, words like incorporates and constitutes, totally different concept and then therefore occurring in a different place. So there's just an actual visual representation of this conceptual space. Okay, so we have the second major link in the chain here. Let's move to the third really link where I think the exponential growth that led to our current day AI began. And that is with the invention of the transformer system. This came out of a paper, published in a paper by Vaswani in 2017. By the way, that Mikolov and Vaswani both came out of the Google Research Labs. And so there was a major limitation to the prior versions of our representation of context and meaning. And that was we only had one representation per word. So if we had a word like bat, as you all know, right, bat can mean a very different thing depending on the context. This is a homonym. So is it the bat that swings or is it the bat that flies? And in the predecessor versions, we essentially just had to aim like somewhere in between those two representations and could not represent them differentially. With the introduction of the transformer, we could then represent the very nuanced context of however a word is used and represent it differently dependent on that context. And the way that it does that, I'll give you two kind of new-ish terms here for some of you, which is this is where these neural layers come into play. And so you can imagine this transformer having, these stacked layers. And as you work through these layers of math, think of it kind of like a learning curve. At each of these layers, when it sees a sentence like, the animal didn't cross the street because it was too tired. When it's trying to decode and understand that, as it moves through the neural layers, it's giving it the more neural layers, the more learning curve it has to try to understand what the sentence really means. And to help it further unpack, it uses what's called multi-head self-attention. And what that does is it actually looks at all the surrounding words in a sentence to try to understand what each word means. So let's look at the target word it here in the middle of the screen. Well, it is actually ambiguous, just like the word bat. So the animal didn't cross the street because it was too tired. Does it refer to street? Does it refer to the animal? Right, that's actually ambiguous. So what this multi-head self-attention does is it looks at all the other surrounding words as it goes and just looks at which words will help it disambiguate how to represent it. So there's those two additional parts of an AI model. We have the neural layers, essentially the learning curve through the model. We also have this multi-head self-attention that allows it to look at all the surrounding words in its context to disambiguate whatever that target word might be. So, just bring it, home here a little bit to our example. So imagine someone approaches you and says, "Hey, nice shirt." Well, that could be ambiguous, right? So what does that mean? Is it really a nice shirt? Do I have a stain on my shirt? Is this a friend? Is this a stranger? We would look at all the context we have for that person to understand what is meant by nice shirt. And for the way these models represent that, I'll just go ahead and go here to the lower left. One of the first models that really was used in application is called BERT from 2019, also coming out of Google. And it had 24 neural layers. So imagine your learning curve is you have these 24 opportunities through these neural layers to learn. You've got 16 attention heads that all try to figure out how to disambiguate each word. And then your 1,000 dimensions, think of those like the latitude and longitude coordinates, but having 1,000 of those at your disposal to very precisely locate the context in that conceptual space. So as opposed to just 2 dimensions, we have 1,000 of those to represent. And that ends up totaling to about 340 million parameters to understand that context. So just a huge leap forward. Okay, so there's our next link in the chain. Let's go ahead and look at our vocab. Just wanted to bring that back. As you can tell, I'm starting to get in some vocab now. Again, we've got the glossary. Feel free to refer to that as we go, or if there's something I'm really glossing over, please do ask the question. I'm happy to define it, but you'll have that at your disposal anytime. All right, so we've got our links in the chain. We're ready for how AI currently today works. So large language models today are very much at the core transformer models as well. So very similar in their architecture. The difference is now that they can be multimodal. So we can represent text and audio and image, all these modalities simultaneously. Another major difference is that we incorporate what's called reinforcement learning from human feedback or AI feedback, which is another layer of training that goes on top to really help it tune in and reflect what humans really want in that output and how to make it more accurate. And this is an important time, I think, to mention now that we're in this world of these frontier models that are really, really big businesses, I think it's important to understand the distinction between open source models and closed source models. So open source is essentially more of a continuum than a binary, but open source generally means that we can get a look under the hood. So if we want to look at all the mechanics, we want to get our screwdriver out and our wrenches and really start changing it ourselves and understanding how it works, open source models allow you to do that. And Llama coming from Meta and Gemma coming from Google are two examples that have some open source elements, including an actual peek under the hood. Are the three frontier models like ChatGPT, Claude, and Gemini are completely closed source. So you can get in the car and go for a ride, but you're not going to get a look under the hood. And another big difference in large language models today, in addition to the old transformer, is that now we have 96 plus neural layers. So we have a lot more learning curve that can take place to understand how to represent this context. 128 plus attention heads, and over 16,000 plus dimensions. So just think of the level of nuance now that these models can have in representing your question, your idea, your context that you've typed in. And that ends up, totaling to trillions of parameters. Okay. So we got into good weeds of how large language models represents context and meaning. Now let's just go through, the basic steps on how an LLM is built. And so, the first step is obviously tons of data. Usually the more data, the better. And again, this open source, closed source distinction is important because the frontier models are actually not going to tell you where they get all of their data. But some of their data is almost certainly coming from the internet. So web scraping, blogs and Substacks, all across the internet. Millions of books from Google. Stack Overflow is a coding site where it can find billions of lines of code, YouTube, Wikipedia, etc. So just a data and lots of it. Then the second major part in building a large language model is what's referred to as pre-training. So in fact, you've already seen that in the acronym of GPT. So in ChatGPT, that's the generative pre-trained transformer. That's referring to this pre-training step. And in the pre-training step, if you might remember at the beginning, I said, well, how does AI really work? And I said, part of how it works is, similar to us in that it's really learning from trial and error. It's learning from making mistakes, trying to fill in the blank accurately. That is what's happening in this pre-training process. It has all of this data, has all of these texts and documents, and it's just removing, words here and there and trying to fill those in accurately based on the answer key that it has. And before it can do that, it actually goes through a process of what's called tokenization. And I really wanted to bring up the token term because you see that all over the place. So let's demystify that. A token is really just a part of a word. So, if we have present tense, past tense, and so forth, a token is just a way to represent, each of those pieces separately. And then again, it's going through that next token prediction or that fill in the blank to really pre-train what's called the base model. Okay, after pre-training, we actually do get a model, a base model. This is a real transformer. This is GPT-2 that was open sourced. But no, this isn't, the current day frontier stuff, but this is an older generation. But I thought it would be helpful for us just to actually watch this happen in real time. So this is the real additional peek under the hood. So let's watch this happen. Let's say I went to the store to buy some. And what you're going to watch happen is, remember that first step is that embedding step. So take our context, or in this case, our prompt or our question, and turn it into that quantitative representation. Then it's going to go through and it's going to do that old context, new context matching. So the old context is it's training data, what it already knows. That's called the key. And then the query is our new prompt, what we're putting in before, which could be something it's never seen before, but it's going to try to match to what it's seen as best it can. So then it's going to do, I'm going to go ahead and generate here. So let's watch it go through. So it's going to do that context matching. It's going to do some additional math. And what this math allows it to do is at the end of this stream, it's simply going to produce a probability. And that probability is just what's the most likely word that it thinks it's going to come next, or the next likely token. And as you can see, if we look through the probabilities here, if you can read those over here on the right, it thought the most likely next word should have been food. But there is some randomization that it does intentionally put in the process. So, in this case, it actually chose to put in a period. Probably not a good move, but that's what it would have done. And I think this is a good point just to kind of take a step back for a moment. You've now watched it go from the embedding representation to matching all of its prior training to what this new prompt is that you see. And you can see at the end of the day, these very sophisticated models are probability distributions. That's what they are. At its very core, they are probability distributions, which means by definition, they are bounded in ways you are not. Right? These are bounded by the training, bounded by decisions made by the developers of these models, just in very specific ways, in many cases intentional ways, that are brains and you are not. So I think this is just a good place to see this is a point of divergence between us humans and AI. So again, you can see some of the strengths and the power of AI, which is right in this section right here. The more training it has and the more sophistication and parameters it has, the better it can represent context. And then therefore, the higher the probability it can then match to that training data. But it's just good to keep in mind, though, it is still limited and bounded by whatever that training data is and whatever the goals of these companies are in getting that probability. Okay, so let's head back here. Okay, so that's the pre-training and part of what you end up with there. The next step is what's referred to as post-training, sometimes also referred to as the alignment process. And that's where they bring in feedback from humans. That could be directly from interaction with their interface. That could be through like mini exams, like a history exam that it has in its input data, and it's trying to answer those questions correctly. That's all part of this post-training process. Often, one of the main mechanisms is called reinforcement learning from human feedback. So that's where that really plays its role. And then the evaluation is really then the final piece. And that can include a lot of the AI safety work as well is going to happen at the evaluation stage. And so at the evaluation stage, you've probably heard of benchmarks before. That's where these benchmarks really come into play. And so think of benchmarks like a goal in coding, a goal in language writing, a goal in a chatbot, answering questions correctly. And so the evaluation is just based on how well it can complete these little mini exams. And new benchmarks are being invented literally every day. And I'll go over, a couple in detail here in a minute. But when you hear state of the art, that is often what that's referring to, is how well it's doing on a particular benchmark. But here I want to uncover something really important, which is ground truth. So ground truth is essentially what AI deems as the correct answer, or in some cases, if correct maybe isn't the appropriate term, the best answer. And it's really important for us to know, where does that ground truth come from? Does that come from humans? Often it does. But which humans? You can imagine, let's say it's a history test. Who decides what the correct answers are? Is it our Western interpretation of history? Is it a more Eastern interpretation? Where is that coming from? Often coming from humans. Sometimes it's coming from AI itself. That's referred to as LLM as judges. But I think we should know that the way these models are tuned and created are all based around however we have defined ground truth, or how these companies have defined ground truth. Sometimes we get access to what those correct answers are. In many cases, we don't. Okay. A couple of benchmarks I think is useful just to see, because I think we can see the connection back all the way back to Alan Turing here. The benchmark here at the top comes from Artificial Analysis. It was actually developed by Google, or not by Google, excuse me, by OpenAI. And then at the bottom is another benchmark platform called Arena, formerly LM Arena. But these are two great places just to check out very specific benchmarks. I wanted to highlight the one here at the top called GDP-Val, because this is one of the first benchmarks that actually put deliverables from real jobs. So instead of being just kind of a, a small little multiple choice test of history, these put actual, like for instance, imagine you're a retail manager and you have a list of tasks that your staff is supposed to accomplish that day. GDP-Val has a deliverable from a real human that produced this and then puts that head to head with whatever the most recent AI model is when you've prompted the AI model to create this list. And the way that it works is you get higher scores, the more likely it is that those two deliverables, that is the one from the human and the one from the model, become indistinguishable. So if that sounds familiar, it should. That is the Turing test. So this benchmark is really the Turing test embodied in real human job outputs. Okay, so now that we know a lot about how important representing context and meaning is to how AI works, just this is a good thing to know about your actual use if you're using it at chat most often, which I think many people are. So it's good to know that the one of the main limitations of how well AI is going to work for you is one that we've already learned, which is it's deciding what that ground truth is. Someone has decided what that ground truth is. You don't always have access to that. But the other one is how well it represents what's called long context. So that could be your entire conversation history on a particular chat. That could be a very long prompt or set of processes you want AI to accomplish for you. It could also include maybe a lot of documents you want it to produce at the end. So you want to know going in what's called the context window. And the context window is just the maximum amount of all those things put together. Again, your instructions, the prompt, the chat history, any uploaded documents, and the total response. So whatever you're asking it to give you. The context window includes all of that. And I just, wanted to put up here in general where that's at for the top frontier models right now. And just to give you a sense, the top models are somewhere between 650 pages of text, about all the way up to 2,500 pages of text. And back in 2023 with GPT-4, that was 12 pages of text. So it just gives you a sense of how far that has come and how important that is to the effectiveness of AI. Okay, let's see how I did. This is really a test of me even more than it is of you. But if you wouldn't mind spending a couple of minutes again, let's see, how well we can answer this question now. Let's make it actually a 5 sentence explanation, five-ish. And I'll put up these three questions. Maybe that kind of help guide you on answering these questions. But let's see where we're at now on how AI works. Let's give you a couple minutes on this one. Yeah, take a few more seconds to wrap up your final thoughts on where you're at. Okay. So what I thought I'd do is just kind of wrap up here. I want to make sure to leave a good amount of time here for any questions you have. I'll just wrap up by doing quick answers to these questions, just to bring us back. How does AI represent meaning and context? So I think now we can use the word embedding, which is this long string of numbers. So this is a quantity, and that quantity can then anchor it in a geographical location in conceptual space. And now we understand the more precision we can get and represent that context, generally the more powerful and the more effective that model is. And that kind of leads to the second question, which is, how can we take one of those components? So let's say it's the multi-attention heads, the neural layers. How do we take those and make it, explain how that makes it better representing meaning and context? And so we'll take, let's say, the neural layers. So taking that actual example, essentially, the more neural layers you have, the more opportunity for learning curve you have to work your way through and actually represent that context in a very nuanced way. So you can imagine moving right through understanding the semantics or the idea of what someone is saying, the grammar, the order of the words, all of those get represented in a much more precise way the more neural layers you have. And really the same thing goes for those self-attention heads as well. And then the final question was, what is ground truth? So again, ground truth in this area of AI is what AI defines as correct or best. This is what the AI is training itself to. So this is what it's trying to reproduce. And it's important for us to know that we, especially for these frontier models, are always going to know how they're determining what ground truth is. And that's why it is so fundamental to understanding how AI works, is that part in particular may be a black box and may not share our values, motivations, or goals in how we're using AI. All right, so I feel like this is a good part to just wrap up my speaking part. If I had to close, I think it's just always a good idea to keep experimenting. These models, their strengths, their weaknesses, their power is changing every day. So, just recommend be curious, keep experimenting, and find how you'd like to use it, in your daily life or professional life. I also hope that by now learning in a hopefully a deeper way of how AI works, you can see the power of you. You can see the ways that AI is bounded and ways that you are not, and maximize whatever that value might be, in whatever context you're using AI in.